Hi everyone, this is Kevin Lewitsky, an Intro to Microprocessors at FAU, and this is my submission for the end of the semester project for the spring 2018 semester. And in this program, we had to read inputs from a temperature sensor, which is here, and then display the temperature in Fahrenheit on the 2-digit 7-segment display, which is here. And this is the microcontroller. This is the Texas Instruments MSP430. Those temperature readings are taken every second, and then every 5 seconds, those 5 readings are averaged and output to the display. So the display is updated every 5 seconds using those averages. When the temperature is below 78 degrees Fahrenheit, the green LED will be turned off. And then using pulse width modulation, or PWM, then the LED is turned on. At 78 degrees, it's turned on at a duty cycle of 10%. And then between 78 and 87 degrees, the brightness increases proportionally with temperature until it reaches the maximum duty cycle of 95% at 88 degrees Fahrenheit. And then above 88 degrees, it stays fixed at 95%. And when the temperature readings decrease, starting at 88 degrees back down to 78 degrees, that PWM signal becomes smaller and smaller. And then below 78 degrees Fahrenheit, the signal disappears and the LED is turned off. So I'll provide an overview of some of the pin connections for the setup here on the breadboard. The 7-segment display contains 10 pins underneath it. One of the pins is to use to control the decimal point, which we're not using for this program, so it's disconnected. 7 of the pins are connected through 330 ohm resistors, which are here. There's 3 on this side and 4 on that side. And then on the other side of those resistors, they're connected to pins 1.0 through 1.6 on the microcontroller. And then 2 of the pins on the display are each connected to one of these BJT transistors, which are here. And those transistors each have 3 pins. One of the pins is called the emitter pin, and it's connected to ground through this black wire here. The other pin is called the collector pin, and that's the one that's connected to the 7-segment display. So those are on the outsides as the 2 transistors are facing each other, connected through these green and yellow wires to the display. And then the 3rd pin is connected through 1 kilo ohm resistors. That's called the base pin. It's connected to these 1 kilo ohm resistors here, which are then connected to pins 2.0 and 2.1 on the microcontroller. The green LED here is connected to pin 2.3 on the microcontroller, and the switch is connected to pin 2.4 on the microcontroller. So pins 2.0 to 2.3 are configured as outputs, 2.4 is configured as an input, and then 1.0 through 1.6 are configured as outputs, and then the temperature sensor is connected to pin 1.7, which is an input, and that uses the analog to digital conversion on the microcontroller. So the entire program is implemented using timers and interrupts. The timer uses the submain clock. That's a high-frequency clock running at 1 megahertz. And it uses the 8 times divider in count up mode. It counts up to 35,000 and then rolls back over to 0. I wrote a function called configure ADC. It configures the analog to digital converter. And those readings are taken from the temperature sensor using input channel 7, since that's pin 1.7. It's configured for single sequence reading, and the sample and hold time is 16 clock ticks for the ADC conversion. So when the program starts, the microcontroller is in low power mode 3, and then when the switch is turned on, an interrupt service routine is activated, and then the program exits low power mode, or the microcontroller exits low power mode, and it moves into what's called active mode. The interrupt is enabled on pin 4 of port 2, since that's where the switch is connected. And during the first 5 seconds that the program is in active mode, the last 2 digits of my student ID number, my Z number, are displayed on the display here. And the last two of my Z number are 7, 8, so don't confuse that with the temperature 78 degrees. That's the last two of my Z number. So those are displayed initially for 5 seconds, and then starting at the 5th second, the program starts taking temperature readings from the temperature sensor. It continues to display the last two of my Z number, 7, 8, for the next 5 seconds, so it's 10 seconds total. And then after that 10th second, those 5 temperature readings are averaged, and then the average temperature is displayed on the 7-segment display here. And depending on whether it's below 78 degrees or above 78 degrees, that LED will be on or off. And then those temperature readings continue to happen every second as the program's running, and on every 5th second, they're averaged, and the temperature displayed on the output on the display is updated. The PWM is using the second timer that the microcontroller has. The period in register 0 is set to 1000 clock cycles, and then the duty cycle in register 1 is just set based on whatever the current temperature is. So if it's below 78, it's set to 0. If it's above 88, it's set to 950, which would be 95%. And then if it's between 78 and 87, then it's set proportionally based on the temperature. So right now what I'll do is I'll demonstrate the program. So I've already started it now, and you can see right now it's in low power mode. So when I turn switch 1 to on, which is here, you'll see that the last two of my Z number, 78, are displayed here, and those will be displayed for 10 seconds total, and then you'll see it display the temperature in Fahrenheit. So right now it's showing 72 Fahrenheit. I'll let it stay here for maybe 30 seconds or so to see if it changes, and then I'll use a hairdryer to increase the temperature so that you can see the green LED turn on. The name of the function that does the temperature readings is called get analog values, and it's called every second using the timer. And the timer interrupt is also what's adjusting the duty cycle of the PWM signal, which is sent to the green LED once it reaches 78 degrees. Okay, and I think I've covered everything. So what I'm going to do now is use the hairdryer to increase the temperature. And I'll try to only get it right to 78 so that you can see the LED come on. I don't want it to get it too high because I want to make sure that you get a chance to see the brightness increase proportionally with the temperature. So right now it's showing 76. I'm trying to get this wire out of the way so you can see it better. It went to 83. Okay, so right now it's on maximum brightness. No, I'm sorry, it's not on maximum. It's on, it's part of the way there. 88 would be the maximum. And it's a little bit hard to see it get brighter and dim. Hopefully it shows up on the video. Because when it goes, you see it gets a little bit dimmer now. And that's as dim as it'll go here. Once it drops below 78, it will turn off. I'll do it again. Okay, so 88 is the maximum brightness. And you can see it getting dimmer now each time the temperature drops. This is actually a really good example because it looks like it's dropping by about 1 degree every 5 or 10 seconds. Okay, so perfect. I think that demonstrated that well. In conclusion, I really think this was a pretty cool project. Because it gave us an opportunity to apply all of the different concepts we learned throughout the semester into a single project that we built from scratch. One thing that I feel much more confident about is my ability to control the different pins. So in other words, to configure them as either inputs or outputs. And then, for example, if they're configured as outputs, like to an LED, to be able to turn that LED on and off. Something that I've done that helps me a lot is rather than using the names of the pins like bit 1, bit 2, bit 3, I actually draw the 8 pins out on paper and then like as if I was doing it in binary, and then I set them to 1 or 0, and then I convert that binary to a hex value and use the hex value in the program. Just because I'm a pretty visual learner, so that has helped me a lot understand what exactly is happening with the various inputs and outputs. And then something else that I learned, or I feel like I've really mastered now, is the difference between logical and bitwise operations. So like logical operations, if I'm doing a logical AND or a logical OR, I'm comparing two things. Whereas bitwise is used like if you want to take two values and you want to assign them. You want to do the AND or the OR on those two values and then assign it, like for example, to an output. So I feel like I've really learned the difference between those two. And then also just with the timers, I've learned a lot about having to do research on the MSP430 microcontroller and how the timers are set up and all the different options you have available. So that was pretty cool too. So that's it. This is my submission for the end of the semester project for Intro to Microprocessors. Again, thank you. This is Kevin Lewitzky. Thank you.